Let's just jump right into this one, guys, because this explainer is absolutely fascinating. Every single day, you probably pop wireless earbuds in, hit play on your phone, and instantly hear your favorite music or podcast. But have you ever actually stopped to think about the literal miracle of engineering happening in that empty space between your phone and your ears? We are talking about your smartphone transmitting around 1 million ones and zeros every single second, completely wirelessly. So today, we are going to demystify exactly how Bluetooth pulls off this invisible magic. And to figure it all out, we're going to peel back the layers step by step. We'll start with the invisible traffic light, then visualize the waves themselves, look at packets and postal codes, break down the channel hopping trick, learn how we avoid microwave chaos, and wrap up with advanced shifting and sending.
All right, moving into section 1, the invisible traffic light.
Okay, so think about how a regular traffic light works. It uses a very specific part of the electromagnetic spectrum, visible light, to instantly send a message to your brain. You see green? Boom, you know to go. That green light has a wavelength of about 540 nanometers, which our eyes easily pick up. Well, Bluetooth actually does the exact same thing. It's just hanging out on a different part of the spectrum. It uses waves that are roughly 123 millimeters long. And because they're that size, they're completely invisible to us. Plus, unlike visible light, they can basically pass right through obstructions, like the walls in your house.
Now, here is where it gets crazy, the sheer speed of all this. When your phone needs to send that long string of binary data to your earbuds, it designates a 121 millimeter wave as a 1 and a 124 millimeter wave as a 0. Your phone's antenna is physically generating these different wavelengths, switching back and forth between them at an unbelievable rate. We're talking 1 million times a second. It's literally blinking ones and zeros. Imagine rapidly flipping between a red and green traffic light, but doing it 1 million times every second. So let's move right along to section 2, visualizing the invisible waves.
You know, electromagnetic waves are pretty complex. If you're picturing a little wavy line shooting out of your phone straight into your ear, kind of like a tiny laser beam, well, you're missing the big picture. Notice how the waves actually travel outward in every direction from your phone, almost like a rapidly expanding bubble or a sphere. And that's exactly why your phone can be buried in your pocket or tossed on a couch facing the completely wrong direction, and your headphones still stay perfectly connected.
Okay, section 3, packets and postal codes.
So with all these spheres of data blasting everywhere, how does your phone make sure only your earbuds actually catch the music? Well, the data isn't just streamed out randomly. It's grouped into highly organized packets. Think of it exactly like sending a postal letter. The first 72 bits act as the access code. Think of that as your exact home address, making sure only your earbuds open it. Then you have a 54-bit header detailing what kind of data is coming, kind of like determining the size of the shipping box. And finally, the payload, holding anywhere from 136 to over 8,000 bits. That's the actual contents of the box, the digital audio you hear. It's brilliant. Just a few lines of code acting as a digital stamp and address.
Next up, section 4, the channel hopping trick. Picture yourself sitting in a packed coffee shop or a busy office. There are dozens of people around you, right? And they're all using Bluetooth earbuds, mice, keyboards, all at the exact same time. How in the world do all these devices share the exact same frequencies without turning into a chaotic mess of cross signals? I mean, why aren't you accidentally hearing the person next to you's music or letting people eavesdrop on your data?
Well, the secret lies in how the spectrum is chopped up. Bluetooth operates in the 2.4 to 2.4835 gigahertz frequency band. To fit everybody in, engineers slice that specific bandwidth into 79 distinct, separate channels.
But here's the kicker. They don't just pick one channel and hang out there. They use a technique called frequency hopping spread spectrum. Basically, your smartphone plays conductor, dictating a highly synchronized sequence. Both your phone and your earbuds hop together from channel to channel. It's exactly like two people perfectly synchronized channel surfing on a TV. If one of those 79 channels is noisy or crowded, your phone is smart enough to just skip it. And as a bonus, this makes the connection super secure, since literally nobody else knows the random hopping sequence your devices are using. And honestly, this part is truly mind-bending. This highly coordinated channel surfing happens 1,600 times every single second. 1,600 hops a second. And after every single hop, one of those tiny digital postal packets is delivered. If a packet gets dropped, your earbuds instantly report back, and the phone resends it. It is constantly, rapidly adapting to the environment around you. All right, moving to section 5, avoiding microwave chaos. Now, you might have experienced this before. You turn on your kitchen microwave to heat something up, and suddenly your wireless headphones start dropping their signal or glitching. That happens because your microwave operates at 2.45 gigahertz, which puts it right smack in the middle of the exact same frequency range that your Bluetooth and even your home Wi-Fi are trying to use. Basically, they're all shouting over each other in the same electromagnetic room. Now, realizing your earbuds share a frequency with a machine designed to boil water might sound a little concerning. But don't worry, it is entirely safe. As the quote on screen perfectly highlights, saying your headphones are dangerous for this is like comparing the blinding light from stadium floodlights to the gentle glow of your smartphone screen. It's entirely a matter of intensity. And as for that microwave interference, your smartphone and earbuds have specialized microchips to aggressively filter out that stray microwave noise. Kind of like how your brain just tunes out useless background stuff when you're looking for a specific street sign.
Okay, final stretch. Section 6, advanced shifting and sending.
So earlier we used that traffic light analogy, switching from one wave to another. But technically your phone doesn't just toggle two separate waves on and off. It uses something called frequency shift keying. This circuitry actually generates one continuous wave, called a carrier wave. It then smoothly shifts that single wave to a higher frequency when it wants to send a 1 and a lower frequency for a 0. If you're a radio fan, you know this is frequency modulation. It's the exact same fundamental science that makes FM radio work.
But Bluetooth needs to be faster, right? So to achieve even higher data speeds, it uses phase shifting keying. Imagine standing on a beach. Frequency shifting is like changing how many ocean waves hit your ankles every minute, say 60 waves a minute. Phase shifting is a completely different trick. The frequency stays identical, still exactly 60 waves a minute, but the locations of the wave peaks and troughs are subtly shifted forward or backward within that time frame. The tiny Bluetooth antenna detects these microscopic phase shifts and translates them into binary ones and zeros. It essentially packs in way more data without needing any extra frequency space. And we can't forget, this isn't just a one-way street. Think about when you're talking on a phone call. Data has to flow back from your microphone to your phone. To pull off this back and forth conversation, the devices seamlessly take turns transmitting and receiving these data packets. They alternate this duty every 625 microseconds. And yeah, they do this all while maintaining that insane 1600 hops per second schedule we talked about earlier. The fact that a microchip, literally inside a device the size of a jelly bean, can pulse, phase shift, frequency hop, and decode these specific electromagnetic waves millions of times a second, it's just an absolute triumph of antenna theory and engineering. It takes invisible, totally chaotic waves and turns them into a flawless connection that we mostly use every day without a second thought.
I really hope this explainer completely changed how you look at your wireless tech, because it is essentially a stunning symphony of physics and computing. And it honestly leaves us with a pretty profound question. If our devices can seamlessly choreograph invisible waves thousands of times a second just to play a pop song, what other invisible engineering miracles are hiding in the gadgets you rely on every single day? Thanks for joining me on this deep dive, guys, and keep your curiosity tuned to the frequencies around you.